Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be talking about shells, because in the next project you will be implementing your own shell. So first of all, what is a shell? Well, a shell is just a thin wrapper around the kernel. Usually it's just a thin wrapper around the kernel. And we've been using shells throughout this entire course actually. You might have realized this, or maybe not. We've been using the bash shell specifically, the born again shell. So to help you visualize what a shell is, sort of comedically here, if we view the shell as a peanut shell, so this is the logo for bash, this is a peanut shell, then the reason why it's called a shell is because it is a thin wrapper around the kernel. So the kernel is within the shell. And we have the Linux symbol here to represent the Linux kernel. So most Linux machines come with bash pre-installed. So let's put the shell back on top of the kernel. And in case you're wondering, the English word kernel literally means the part inside of a seed or nut. Okay, so we can pass commands to the shell for execution, but how does this actually work under the hood? Well, the shell is not reading plain text that we're passing in, at least not directly. The shell is encoding this information as integers. So to demonstrate this, if I show you this program I've defined here, this script ls-l.sh. This is just a shell script I can run. All it does is run ls with the -l flag. So I can run this with bash, and you can see we actually get the expected output of just our current contents of our directory. Now let me open tmux here so I can split my screen horizontally. And I can use the hexdump utility to actually view the hexadecimal or the integer contents of this file as hexadecimal. So I can run hexdump on ls-l, and you can see the hexadecimal contents. And for improved clarity, I could put the -c flag here, capital C, for canonical output, so I get the hexadecimal values on the left-hand side here, and the canonical or the text ASCII decoded text here on the right. So one more thing I guess I want to mention here, just as a refresher, I think I showed this before, but you can actually use HD. It's an alias for hexdump-c, and we get the same output. Now, to prove to you that this is in fact these hexadecimal numbers are in fact equivalent to this ASCII output here, I can open up the man pages for ASCII, and if I scroll down, there's a table here. If I look for the value 6c, so this is the hexadecimal column for 6c, so if I scroll up you can see it says hex right here. So I'll go back to 6c now. This corresponds to the ASCII English character L. And of course the first character in this string is L, and the first character here is, first byte sequence is L as well, 6c, which corresponds to L. And the last one's also L, and you can see it's also 6c at the end. So this is just to prove to you that the text we pass to the command line is in fact just numbers under the hood, integer values. It has no inherent structure. Even if we were passing just literal characters, which I guess we're passing chars, technically, that's the kind of number we're passing, but even though we're passing individual numbers, even if we were passing letters somehow directly to the command line, the command line would need a way to process these letters and interpret them as commands. So the general process of doing this looks like this, where we have this do while loop. So the first thing we do is take user input, we parse it. So I'm going to talk a lot about parsing later in this lecture, but parsing is basically a function that converts unstructured textual input into a structured format. That's what parsing is in general. And we save this result in a variable we're calling commands, and then we run those commands, and we keep doing this until we receive an exit command. So how do we actually process these commands? Well, let's take a high-level view here. So we're doing this read eval print loop. So read, evaluate, print. Shells are often called REPLs sometime because of this acronym, read, evaluate, print loop. So sometimes you'll hear shells referred to as REPLs. And in this read step here, what we want to do is process input like this. So I'm going to draw a box here to help us visualize this, or what we want to do. I'm going to separate each of these components think of them like words in an English sentence. There's a special word for these called tokens. We'll see that more later, but so I'll start calling them tokens now. We want to separate these tokens of this command from each other. And these can be separated by white space. So maybe you have like some white space here, some spaces and tabs. We're not going to count new lines. New lines are going to be special in how we parse commands. But for now, you can think of this as having some tokens separated by white space. So some tokens are separated by white space. And we can do more than just commands and their arguments. We can also separate a command from its from special symbols like redirecting operators. So here we're having a redirect out to out.txt. The redirect symbol is special and separate from the ls command name, and the redirect destination is also its own token. And what's important to note in this example is that there's no space between these tokens, at least I'm trying to represent that here, no white space between them, but our grammar, which I'll define grammar later, our processing tool needs the ability to distinguish between individual tokens regardless of whether there is white space. And we can do this as well by just, we can also separate pipe symbols as well into tokens. I'm not going to draw this one, but I think you get the idea. So, parsing commands. What are the, I've kept saying the symbols, tokens. What are the individual symbols we have when parsing commands? So we have the text for a redirect out, a redirect in, the vertical bar for a pipe, the string, this is going to be any contiguous sequence of none of these three characters, and \n for a new line character, which signifies the end of command. This is so that when you press enter on your keyboard, the command gets sent to the shell. In whitespace, again, it's not a proper symbol or a token, it's just what we use to separate the arguments from one another, separate the tokens from each other. And now here's an example of a grammar that we can use to define our language for our shell. So I'm going to be showing an example of how to actually use this, but first just to give a description of what's going on. Each name on the left-hand side here is a symbol, and each symbol has a production. So that's what this double colon equal sign means. It means the production follows. And in the production, we can have another symbol, or we can have a literal, a token piece of text, a piece of text that is like a atomic token, I suppose you could say. And the way this parsing is going to work is that it's going to be recursive. So if we want to parse the symbol start, we have to parse the symbol pipes. If we want to parse the symbol pipes, we have to parse the symbol command, and then pipe star. And pipe star means 0 or more of the pipe symbol. On the other hand, the question mark symbol here means 0 or 1. So I think I've talked about this enough. Maybe it's best if I just start illustrating how we're actually going to use this notion of parsing. Now for this assignment, you're not going to have to form a, what I'm going to do is form a tree output, and you won't have to do this for your current assignment. But I think it's very useful to know this, especially because in the second half of this course, you will be needing to work with parsed tree abstract syntax trees, as they're called, parse trees. So I think it's a good idea to review this material now. So let's take a look at how we would actually parse this input here on the right. So let's start by writing the name of what we want to parse. We want to parse the symbol start. So we'll start with that. Make that a little bit bigger because that's kind of small. We'll start at the bottom. And to parse the start symbol, you need to have a \new line and the pipes symbol. So I'm going to draw the pipe symbol here. Pipes, and we'll draw a line connecting the pipes symbol to the start symbol. Then the pipes symbol, or I'm sorry, the start symbol ends in a \new line, so I'll draw that now as well. We'll draw that right here. Make it a curved line so it's not quite in the way. And the pipe symbol, so now we're on to pipes. To parse this, you need a command. So we'll add a command here. We'll drag it over here. Oops. We'll connect the two. So we'll connect this here. Command. and then any number of pipes. We'll get to the pipes later. First, we'll parse command. So to parse a command, you need a program. So we'll draw a line there. And what we're doing is called top-down parsing. There's also bottom-up parsing, but top-down is usually a little bit simpler to implement. So we have a program here, symbol. The program symbol consists of a string and then any other number of strings. So let me actually draw this a little bit closer. So we don't have any other strings, so it's a string, which is going to represent the name of the program we're running, and then any number of strings which represent the program's arguments. So for the example cat here, we have no arguments, so we can just connect cat to the string, treat cat as the string token directly. And that's it. And then that's all we need to pass to this program that we're parsing, or program symbol, I should say. So we parse the program. Now back up to command, we have to parse a optional in redirect and optional out redirect. Well, we can already see there's no out redirect, but let's look at the in redirect. There should be a redirect in symbol, which there is, so I'll draw that now. Make that line a little curved so we can get some space here. Okay, and then a string should follow. That's the name of what we're redirecting our input from. The name of the file we are redirecting our input from. So I'll just copy this, drag it over, so we can redirect the string. And that forms a in symbol. So I'll put this here, in. We can connect this like so. So these two components, these two symbols form in, and then this in helps form the program symbol. So we have no out, so we've finished parsing the command, so the whole command is now formed. Actually, sorry, this in symbol should connect to the command, not the program, because we can see from the grammar that it goes as part of the command's production. So we parse the command. Let's go back up to pipes. So in pipes, we have a command followed by any number of pipe. A pipe is the vertical bar, which we have here. So I'll copy this over, change the text here to a vertical bar, move this over just slightly, there we go, and then followed by a command. So we already have most of the tree structure here for parsing a command, so I'm just going to copy this over and drag it underneath the WC command. Oops, drag it over a little bit more. That should be better. Yeah, now I'll move these things around so they're nice and aligned. Okay, no program there, move the command here, and now we have our second command. And so we parsed our command, there's no more pipes, so we are done parsing the number of pipes. And now we have our start, actually, we finished parsing pipes actually, the pipes symbol. And we have finished parsing the start symbol, as well. So now we've actually created a full parse tree of this input. And for this project, you won't have to form a parse tree, but you will need to understand how to read in tokens to form structured input. We're going to be forming a list of commands that you'll be executing. So the parse tree is not really necessary for this project exactly, but it will be coming up later in this course. But the idea of reading in input one token at a time is going to be very relevant for this project. And this is just some more explanation of the different terminology, the different metavariables and symbols in the grammar. And here we actually have some pseudocode. So the big idea is that you just go outside in. So we consume one token first to prime the pump, so as it were. So what this will look like in practice will be something like this, where we start with our token on the outside of the program. It's one token before, basically. And then when we consume one token, we'll move this symbol over here. We'll match against the start. So we started the start symbol. We try to parse the pipes, try to parse a command. Parsing a command involves matching a program. Then we consume one or more strings, so we advance here. We match an optional in redirect. If next token is the in redirect symbol, consume it, okay. And then a string token, so we consume the string token as well, okay. Match the out, there is no out to match. And match pipe star if next is a vertical bar, which it is. Then consume it and repeat matching a command. So we consume it, then we match a command. So we go back up to here, perform all these steps, match another command, and then match in backslash new line, and we're done. So that's it. That's pretty much how the implementation works. You just start going top down, which is why it's called a top-down parser. Okay, so how do we implement this? Well, good news for you, for this project, you're not going to have to actually tokenize the input. So the process of converting raw text into these tokens is called tokenization, also called lexing or scanning. You don't have to implement that. For this project, we're going to give you a lexer, which will be generated for you using the program Flex. So lexing is a very well-studied, lexing and parsing really, is one of the most well-studied fields of computer science. It's so well-studied that we have tools like Flex, for example, and Bison and Yak or some other names of tools that can just take in and input a description of a grammar similar to this and just generate a lexer for you. And we'll be seeing that later on in this lecture. But basically, you don't have to implement the functionality for turning this token stream, or character stream, I'm sorry, this input of characters into these individual tokens. So you're going to receive an input that's basically has all these red boxes here. These words are divided up for you already. And there's these following types of tokens are what you're going to be working with. So you can see these correspond pretty neatly to the grammar we've been working with so far. So we have our string here. It's a string, vertical bar is a pipe, redirects, and end of line. There's some global variables, and at this point, now I think it's a good point to actually show the code. So I'm going to hop on over to my terminal here, open it in my window on the right. I'm going to zoom out a little bit. And let's take a look at the code. So I have this code downloaded, and for the proc project, you're going to be starting with this exact template code to begin with. So we're going to download a tar file using a command that we're going to give you, and you'll unpack it, and you'll start off with all this beginner template code. So you don't have, this is what you should have when you begin working on the proc project. So you're not writing your own makefile. So let's take a look at what you're going to be given. So actually, first what I'm going to do is copy this myshell.template.c file to a file called myshell.c so we can start begin working on the project. So I'll open that up now. And the first thing we'll have is a bunch of includes. You don't have to worry about them. And we're going to include also, well, these are system includes, I should say. The first non-system include, a local include, which you can tell is a local include, and by local I mean in the current directory. You can tell it's a local include because of the quotes here. So system-wide includes are enclosed in tags, local includes are enclosed in double quotes. If we go to this file, so I'll press GF in Vim to go to file, you'll see that the types of tokens that are defined here match exactly what we have in this table. So that's very convenient for us. So I'm going to go back. And there's this util.h file as well. This is not defined by Flex or any other tool. This is something that we actually, Dr. Gazillo in the past, wrote for this course. It's just a few helper functions for you for writing this, for completing this project. You don't need to understand how it works, but if you wanted to, you could edit the file util.c or just view it, and you can actually see the implementation of all these different functions. So that might be interesting for you to look at. So let's go back. So Control-O to return to the previous destination, Control-O to return to the previous jump location again. And now lex.c. So if I try to go to this file, gf, you'll see I get an error at the bottom of my Vim screen. Can't find file lex.c in path. That's because that program that I mentioned earlier, Flex, is going to generate this file for you. And the way Flex generates this is based off of this file lex.l. So if I open this file up, you can see this is the Flex specification of the grammar that we are trying to operate with. So we're trying to parse, I should say. So you don't have to understand the syntax. It's not really necessary for you for this course. But basically, we're just returning different token types based off of what symbols we see in the input. Let's go back. All right, so now onto these global variables that I had stopped at previously. There's two that we're looking at here. This is a token variable called lookahead. This is a global variable. And a char star variable here, a string essentially, called lexeme. So what is a lexeme? Well, the lexeme is the text of the current token, and look ahead is just whatever the next token is. So this is storing the next token in the input, and I said current, I meant to say next. So this is the text of the next token and the next token's text. So for this example, if we have this pipeline here, the tokens would be as follows. So ls is a token, but its lexeme is the text ls. And it's called lexeme because the lexer is what's producing it. I think that's why it's called lexeme. So how do we get these global variables? How do we populate them? Well, we use this function called consume. And consume is going to be defined for you. Actually, it's defined right here, you can see. So if we call consume, what that will do is use this yylex function, which is given to us by flex. That'll be in lex.c. So that's automatically generated for us. It will populate the value of the look ahead token, and then we will have text as the current text of the token, and we're just going to copy that string over into this lexeme variable here. And again, text also comes from the lex.c, which is automatically generated. In addition to these, this consume function, we have these helper functions ensure and match. And what these will let you do is check whether a token in the input matches what you expect at a current time, and if it doesn't, your program will just crash, which is helpful for syntactically invalid inputs. So for instance, if I type at the command line something like cat redirect in from a pipe out.txt, this is nonsense, right? It's not syntactically valid. You can't redirect in from a pipe. You have to specify a file name. So if I were to type this in, you can see that we get a syntax error. And if I said in.txt, this would still be actually invalid because there's no in.txt file that exists, and the program out.txt is not a command. So I could probably fix this by saying myshell.c, and then that would be syntactically valid. So ensure lets us crash in case of syntax violations. On the other hand, match lets us check that a token matches what we expect, or what we might see in the input, might expect in the input. And instead of crashing, it just returns true or false. So this allows us to parse optional elements of our grammar, like how we saw earlier up here, how in and out are optional elements because there's a question mark next to them. The match function lets us implement that functionality of checking for optional symbols. So let's actually start looking at some code here. So I'm going to scroll down to the parse function. So these are the two functions you're going to be filling in as part of this project, the parse and run commands functions. And you can see in main, all we do is just call them. That's all we do. Just parse the function, parse the input, and then run commands. So let's actually fill in some of this parse code with some template code here. I'm going to copy this. I'll VIP to view in paragraph, paste this in. There we go. Well, let's see what we got here. So the first thing we're doing is consuming the first token in the input. This matches the pseudocode where we're priming the pump, as it were. So I'll go back to what we had here. We consume the first token. So our look ahead token is currently here at cat. And what you'll need to do is fill in these to-dos as part of the project description. And then we ensure that the first token is a string because the first token should in fact be a string. If you look at this grammar here, if we walked all the way down this grammar to the leftmost node in the tree, so actually if we go back to the diagram, you can see the very first token needs to be a string. So that's what we're ensuring here. And then we're ensuring this here as well. I'm not sure why. So Dr. Zillow originally wrote this code. I don't know why he had two ensures. I think just to be very certain that the first token of the program symbol is a string. And I just want to mention this. We're using these go-to labels just to demarcate the different parts of our parse function to make it very clear what symbols each part of the function is responsible for parsing. You don't have to use go-to labels if you don't want to. You could implement this in a different way. You could just replace these with comments like so, just to signify what the different parts of the parse function are parsing. But for now, we're just going to leave these go-to labels here. All right. So we're ensuring that the current current token is a string, and then we're consuming it, so we're moving on to here. And we don't collect arguments, so we're not going to do that. And we are also not parsing any redirects in. We are checking for a redirect out, so we're checking if the next token is matching with a redirect out. So this actually would be invalid because our next token is not a redirect out, it's a redirect in. So what we should do, let me scroll down here, I'm going to copy this marker here. Let's say our token was currently here, or our marker was here. We reached redirect out. I'm sorry, it should be here. We parse we consume the string. First input, we consume the string. Now we are matching the redirect out symbol. We match that here. So then we consume that token. So we advance to the string. We ensure that the current token is a string, which it is. We consume that token. And then we advance to the next token, which is the end of line character. And so we finish parsing the string. So if I were to run this program, I'll run make and then run mysh. You can see we're actually put into a shell where we have to enter a command. This is just reading from standard in. So if I were to type ls out.txt and press enter, it actually works. So we get no output because all this is doing right now is doing what is called recognition. So this is a recognizer. We're not actually converting the input to any structured format. We're just validating that the input is in conformance to the grammar we've written for this language. So right now, we shouldn't see any output. We should just see that the output is correct. Or we should just see no errors if the output is correct. And we could actually run other commands, so I could just run ls by itself, and that would work too. Now, if I tried to run something different, like let's say ls and then give ls an argument, ls dot, we'll get a parsing error. And the reason for this is because we haven't implemented arguments yet. You can see in this code on the left here, there's a to-do to collect the arguments, and we haven't done that yet. Also, if I were to run ls and then pass in, let's say, well, maybe ls is a bad example here. If I were to try and run cat and redirect in from myshell.c, you can see there's a parsing error as well because we have not implemented redirect in. So to give you an idea of how this working on this project is going to go, let me open this back up now. What you'll want to do is work on one element of the parser at a time. So I strongly recommend not trying to tackle all these to-dos at once. You should work on one of the to-dos at a time, test that that new functionality works, and then proceed to the next to-do. And if you want to be very clean about this, write a commit every time you make one of those changes. That way, if you find that one of the additions you made actually introduced a bug into the program, you can just go back to the previous commit before you added that buggy parsing functionality and fix your code. So to show you how we could potentially add on to this parser, I'm going to use VIP to view in paragraph here. Select this paragraph, Shift V to select this line, paste it in, CW to change the word. We're going to change this to in, and we're going to change this symbol redirect out. So I'm going to press X to delete this character, capital R to go into replace mode, type capital IN to redirect this to redirect in. And suddenly we are able to parse inputs now as well. So let me quit this, and then we can actually run, or let me actually run make. And run the my shell again. And now if I do the example from before, catting my shell.c, you can see actually it works. It no longer crashes. So some of the inputs will not be that hard to parse, I think, as long as you just try to use what we've given you as an example. So again, there's no output. We're just validating that commands work. The way we're going to be generating output is by storing the commands in this command T struct. So let me actually jump to that now. I'll open up my shell and we'll edit util.c so you can get a good look at this. Command T, let me actually go to the definition. Actually I think it's defining util.h, so let me hop over there. Command S, alright. So this command struct has an array of char stars. This is called argv, which is going to store the arguments for this command. The first argument, the element at index 0, should be the name of the command we're going to run. And this char star to in should store the name of the file we are redirecting input from. This char star out should store the name of the file we are redirecting output to. And if there is no If there is no redirection in or no redirection out, these should just be null. And this is going to be a linked list structure. These commands are going to form a linked list structure. So we have this struct command s next here. This pointer to another command in this next field here. Personally, I don't like linked lists because they perform very slowly. They're not computationally efficient. But for the sake of teaching and for this course and for this assignment, it's easier to work with linked lists than with faster alternatives. So we'll be using a linked list structure for this assignment. All right, so let's hop on back. How can we actually use this command struct to store our commands? Well, that's what you're going to have to be doing for this assignment. You're going to have to be populating this struct with your commands. So the way we can do this is by calling this add command function to create a new command. So let's try doing this here. We'll say, after we've ensured that the input is valid, we'll say command t pointer command equals add command. All right, that should create a command. Let me actually try running this to make sure I didn't mess anything up. I'm actually going to open this in tmux so I can split my screen. Shell.c, we'll run make. Okay, compiled, that's good. And we have that here. Okay, let me split my screen, so I'll split it horizontally. And we'll try running our shell. And if I run ls, it just works. Okay, so it seems like it didn't break anything, so that's good. And to create this command, what we're going to do is populate its individual fields. So here we are inside a redirect in. So if we have successfully consumed the in token, then the next token in the input, the look ahead, should be the name of the file we are redirecting in from. So to implement this, we'll just say command arrow in equals lexeme. And actually, one more thing we should probably do, because you've ensured there's a token here, or that there's a program name here. Let's assign the command argv0, so the name of the command we're currently parsing should be lexeme as well, because we've just ensured that we are on the first string in the input. So I'll go back to the diagram here to show this. Let's go from the top. We call consume once to prime the parser, set it at the ls here. So our look ahead is on ls. We call ensure to make sure that we are in a string, which we are. Then we create a new command. So I'll just create that command here. I'll make it red. Make it a little bit bigger. And the commands, let's see, it's argv. We'll set argv0 to just ls. That's what this line here is going to do. And then we consume that token. So we'll go over to this token next. Now we're going to match a redirect in, but there is no redirect in this input here. You can see there's only a redirect out, so this line's not going to execute. This block is not going to execute. So we'll proceed to out. If we match a redirect out, which we do, then we consume that token. Okay. Then we ensure that the look ahead is a string. It is. And then what we'll want to do to populate the in field of the struct is set the command in field to out.txt. And it's out field because we never specified the out field. When we call add command, it will initialize everything to null for us. So you don't have to set things to null explicitly. So what you could do, for instance, if you could say like else command dot in equals null. But you don't need to do that. You don't need to do this. So you can delete all that. This add command function, if we were to go to its definition, util.c, you can see add command. It actually just sets these fields to null initially. So you don't need to initialize things to null if they're not present in the input. You can just focus on populating fields that do exist. All right, so we specified that the program's name is ls. You skip the input, and we've set the output. Let me actually fix this. This is reversed, so this should be in. This should be out. There we go. All right. Sorry for that typo. Cool. Okay, so now we consume this token here, consume that token, and then we check that we're at the end of line, and we are, and so we're done. And you'll have to implement support for parsing pipes here as well, so keep that in mind. And now what we'll do, let's try running this. So I'm going to save my changes, run make. I'm going to quit this here. And let's run my sh, and we'll try running ls out.txt, and it works. And to verify that it works, you can call this other function down here, print commands. This is one we're going to give to you, or giving to you as well. And what this will do is, given some input, no matter how spaced out it all is, it will, oh, I forgot to run make. What print commands will do is actually print those commands in a pretty printer form. So I think I actually made a typo here somewhere in my code, because it seems like we're getting the wrong symbol printed out. So let me fix this. Let's see. This is redirect in. So I specify, yeah, here's the problem. I set the in field of command to Lexi when it should be the out field. So now if I run this, save and quit, run make, and then run my sh and do the same thing as before, you can see it actually pretty prints the output correctly. So that might be a bug you will encounter. So hopefully you actually won't encounter it now, because you just saw me fix it. Okay, so let's go back to the input here, or the slides, I mean. You can also get the first and last commands that have been parsed with these first and last command global variables. You may not need to use them at all. They're useful. The add command function just uses them to add the latest command you're parsing to the end of the linked list chain. So you don't need to manually assign the next field of your commands that you're building, the chain of commands you're building. That will be done for you when you call add command. All right, so let's see how we could actually actually, this is the rest of the parser, which I think I already wrote, so we can skip this for now. And again, you can use print commands for debugging purposes. You don't want to call print commands in the final project, because it's just going to print to, I think, standard out or standard error. I'm not sure, but we're not trying to print the contents of the commands, though. We're trying to actually run them. So how do we actually run these commands? Oh, I guess one more thing you could do that I want to point out before I get into running commands. How to automate some of this testing. So I can actually copy what's here on the left-hand side, echo ls to ls.out, and pipe this to my /mysh, and this will actually just run our, currently a pretty printer, run our pretty printer. And the reason this works is because we're sending this line of text directly to our shell to execute. And remember, our shell terminates when it receives a new line character. So this works here because echo actually implicitly inserts a new line character at the end of a string by default. But if I were to type in -n, add the -n flag to echo, which would prevent echo from adding the new line character to the end of its input, what do you think would happen? So we're going to send this text to mysh without appending a new line character. Well, if I run this, we get a parsing error, because remember, our grammar requires that our input ends in a new line. So if we don't have that new line at the end, it's just a parsing error. Because instead, the parser receives an end of input, which it's not expecting. So I would say you could probably actually put a few of these commands, these echo to mysh commands, in a make file, and you can automate some testing that way. Yeah, so this is just another example. You could also save those tests in scripts and just run them, but I would recommend just putting them in a make file. All right, so how do we actually interpret and run these commands? I've been trying to get to this whole lecture. How do we actually run these commands we've been parsing? So the way we do this is to essentially walk the list of commands and then use the syscalls you've been reviewing so far in this course, fork, exec, dup2, pipe, etc., to actually execute this command chain. So let's open up our file again, mysh.c, and I'm going to try and copy over. So this is like the pseudocode for doing this, but let's try and copy over some sample code we have here. I'm actually going to not copy it from there. I'm going to go to the course. Well, actually, so I tried copying this earlier from the course website and from these notes, and it didn't really work. So instead what I'm going to do, there we go. All right. So we were able to copy this in. I'm going to have to cut the video because it took me a while to get that working, unfortunately. But we have our input copied in here, and or this run commands function copied in. And what we're doing is we're walking the chain of commands in that we parsed. So we're getting the first command, and here we're actually checking if there's only one command. So we're saying if the first command is not null, and there is only one command in the input because the first command is equal to the last command, then we'll execute this method of executing the pipeline of the command, I mean. The reason we have this in a branch is because when you parse the input, you're going to have to support pipes. So you might have to implement pipes in a different way than the way we've implemented parsing or executing one command here. So for executing one command, we are just going to get the first command in the list, use the classic switch fork idiom to create a child process. Within the child process, we're going to use, let's see here, execvp to execute that command in the child process. And if the input has a output, if the command has a output redirection, then we will use this code here to redirect standard out to that output. Now, you'll notice that this lacks redirection for standard in, so you're going to have to implement that yourself. And in the parent process, we just wait until the children finish running. So that's what this loop here does. It will just wait until wait returns an error. That's what this line of code does. And then once it does return an error, it ensures that that error is eChild, which means that wait returns an error because there was no more children to wait on. So there's these 4 lines of code, or 3 lines of code. Just wait until there are no more children to wait on. All right, so let's try running this. So let's say /mysh, or I'm sorry, run make first, mysh, and now if I run a program like ls, it actually runs. So that's pretty cool, I think. So for your project, you're going to have to add more functionality to this template code, to the starter code, but I think you should be good to begin working on it now. So good luck. If you have questions, please reach out to me, and I'll see you all in class.